All right, well, as we get started today, I first of all want to say, in my students' defense, they just came off spring break, so they haven't been thinking physics for a little while. Let's see what they remember, though. Obviously, if you've been watching these lessons in order, close together, you should at least benefit from this very thorough review we're about to have. But I've got to get their brains thinking physics because we've got a quiz coming up in just a few minutes over the first couple sections of Chapter 19. Chapter 19 talked about the reflection of light. Remember, we said when light strikes a surface, some of the light's absorbed, some of the light's reflected off. If it's transparent, light could go through and somewhat reflected, like a window. Right? You see a reflection in a window, and you can see what's on the other side oftentimes. And some light may even be absorbed by the window. Certainly a tinted window, that's going to be the case. Some light will be absorbed, and then light can be scattered as well, depending on the surface. So a lot of behaviors, but we were focusing on the reflection of light, and we're looking at light as a bunch of individual little rays that strike a surface coming in parallel together. This study of light in general is called optics, and the study of light, treating it as a bunch of infinitely thin, infinitely parallel rays that travel together, class, that's called geometric optics, because we were able to deal with angles and stuff when we treat light as rays. We said not all the light that strikes a surface reflects off, only a part of it. If we made a ratio of how much light reflects off compared to all the light that hit it, that would give us something called reflectance. Now remember, we express reflectance in terms of percentages, right? 98% reflectance or 1.6% reflectance for some of that stuff that reflected almost nothing. You could really tell what was being reflected. So reflectance is that ratio of reflected light to total light. We said that when light strikes a smooth surface, the light rays that hit the surface parallel stay parallel as they reflect, and therefore you see a clear image. What type of reflection is produced by smooth surfaces? Specular reflection. Now, an uneven surface, a rough surface, is going to cause parallel light rays as they strike the surface to scatter in all directions as they reflect off. So you don't get a clear image. The light is still reflected, you just don't get an image produced. That's called diffuse reflection. We said we have two laws of reflection that we got to play around with quite a bit back before spring break. One of them says that the angle of incidence, class, equals the angle of reflection. So that, and these two angles, by the way, are measured from the perpendicular, called the normal, right? And so that was the first law of reflection. The second law of reflection said that the angle of incidence, the angle of reflection, and the normal all have to lie in the same plane. So that if you want to redirect a light ray, you have to change the angle of the mirror until you get it just right, and then it wobbles or something happens, or the sticky tack stops holding. And anyway, angle of incidence equals angle of reflection, and those three rays are all in the same plane. When we talked about plane mirrors, a plane mirror just means a flat mirror, good, just a flat mirror, a normal mirror that we would normally use. We said for a plane mirror, images appear to be on the other side of the mirror. I remember my grandparents had this little bitty house. It was just the two of them, no reason to have a big house. It felt big, and it dawned on me one day, it's because their entire wall, it had a vaulted ceiling and everything in their living room, but the entire wall had mirror on it. There was like 3 or 4 panels of mirror on that whole wall. And so the room looks really big. It looks twice as big, in fact, as it really was. And it gave that illusion. A bathroom. Have you ever been in a bathroom when the mirror was off the wall? And when my dad was painting the bathroom when I was a little kid, he took the mirror off the wall. Like, this is a really little room. I never thought of it as little before. But man, that mirror gives the illusion of a bigger space. But the images appear to be on the other side. I don't know if I ever finished the question. What do we call images that appear to be behind a mirror? Virtual images. And all plane mirrors produce virtual images. What else do we know about the images formed by a plane mirror? Call them out.
Inverted. No.
They're not inverted. Rather, they are like, you don't look in a mirror, man, I'm upside down. They're upright as opposed to inverted. Okay, so they're virtual, they're upright.
Unmagnified.
They're unmagnified. Is that what you just said? Okay.
Reverse.
They are reversed. Not inverted like upside down flipped, but reversed. Again, we said along the z-axis, so the right hand, left hand kind of thing. And we can undo that with two mirrors, or an even number of mirrors in general. The final thing was, because not all the light that hits that mirror is reflected off, The image is slightly darker than in reality the object is. And so that was for a plane mirror. And the math of a plane mirror is everything's cut in half, right? Remember we looked at the lady with the bonnet. Miss Morse was very confused when she came in later. What was that thing with the thing on its head? That was a lady with a bonnet on top of her head. She's like, that was a poofy bonnet. Yeah, it was. And anyway, so, but remember, we just basically said from where the eyes are to where the top of the head is, since the angle of incidence equals the angle of reflection, halves. It's got distances in half. So your height with whatever heels you might be wearing, the height of whatever hat might be on your head, thinking maybe graduation. If you wanted to see yourself full length, take your total height, cut it in half. That's how high the mirror has to be. Halfway between your eyes and the floor is the bottom of the mirror. Halfway between the eyes and the top of the hat is the top of the mirror. Pretty easy math for those. Then we got into mirrors that we don't use on a regular basis, or at least we don't think about them very often. And these are mirrors that are part of a ball, so to speak. We call these in general spherical mirrors. Two types. If the ball has the reflecting surface on the outside of the ball, and you cut off a piece of mirror, we would call that mirror a convex mirror, where the mirror surface is on the outside of the curve. Or one that bulges outward would be another way to say it, because you might be vexed if you were bulging. If the reflecting surface is on the inside of the sphere, and then you cut the sphere off and piece off, and hey, there's the reflecting surface on the inside, class, that's a concave mirror. Now, technically, are spoons perfectly concave or convex? No, because they're not perfectly spherical, but you kind of get the idea. Inside of spoon, concave, back of spoon, convex. The center of the surface of the mirror is called the vertex. The center of the ball, or the center of the sphere, is called the center of curvature. And if you were to draw a line through the center of curvature and the vertex, you'd have something called the principal axis. And when we drew our ray diagrams, remember, we would have that principal axis line. The center of curvature was usually the second dot. There was another dot in between dot one, or furthest dot, and mirror surface, which we just drew as an arc. And that's where the light, in theory, if you had like the sun or another light source a really far distance away, infinite distance away, the light rays would all approximately converge at that point called the focal point. How do we find that focal point? If we know the center of curvature, the focal point is always halfway there, right? It's that midpoint, if you will. It's half if we would, and now that distance from center to the mirror, or to the vertex, for instance, is called the radius of curvature. Think of it, the big ball of mirror, the dead center of the sphere is the center. At any point on the mirror surface, or any point on the ball, that'd be a radius length. So the radius, and then from the mirror to that focal point, we call that the focal length. So the focal length then must be half the radius. That was the first little equation, if you want to call it that, is that focal length equals half the radius of curvature. We're going to come back and revisit that idea in a little bit when we get to the math of spherical mirrors after the quiz. We said that if we wanted to draw ray diagrams, we use three principal rays. Remember one of the three principal rays? The parallel ray. Remember that ray was parallel coming in, but when it hit the mirror, it would reflect through the focal point. Now again, that's assuming everything perfectly converges at the focal point. We know that it doesn't, as we're going to get to in a moment. Another ray. Central ray. And that ray just goes through the center of curvature. And because it's traveling along the radius, it'll reflect right along itself. The final ray was the, and that was the ray that we directed through the focal point. So once it hit the mirror, it would reflect parallel to the principal axis. And we used some of those ray diagrams. The book used ray diagrams to show what would happen. We said that for a concave mirror, 6 different things can happen when light strikes the mirror. Again, if the light source is an infinite distance away, class, we just get a little speck of light, a point image. And where would that point image be? At the focal point, theoretically. If the object comes in closer, but it's still behind that center of curvature, that second dot, you're going to actually get an image now. But what's true about that image? It's real. It's not upright. It's inverted, and it's small, or we would say reduced. So the object may be this big. Maybe we have a really big mirror, and there's Kendall standing way over here, and then over here we've got the mirror. We would see a little bitty upside down Kendall. If we put our eye in just the right spot, we would see it. So we get this little bitty upside down Kendall. Real, because the light is actually going to reflect off the mirror. it's going to be inverted. By the way, all real images are inverted, so she's upside down, and reduced. Now, if you brought Kendall a little closer, and we put her at the center of curvature, now what's going to be true about the image? Real, inverted still. Now it's unmagnified. It'll be the same size. It'll just be flipped upside down. Continue to bring Kendall closer. What happens to the image? It's going to be enlarged now, but it's still real and inverted until you get to the focal point. What happens at the focal point? You don't get any image form. She's infinitely large, infinitely far away. You got nothing. All right, well, what if you continue to push Kendall even closer to the mirror? She now comes in front of the focal point. Now what happens to Kendall? It becomes a virtual image, appears behind the mirror, upright, and enlarged. That's that cosmetic mirror use, right? You stand in front of the focal point to see your face in a cosmetic mirror. Those are the 6 cases of concave. Convex is easy. There's only one thing a convex mirror ever does with light. It always produces object and mirror closer they appear, store mirror. No. Virtual images that appear to be inside the mirror.
Same thing, bigger, smaller.
So you look in the mirror, do you look big to yourself in the store mirror? No, you always look smaller. So reduced. So real, reduced, and for the sake of the employees, it's a good thing they're upright, right? Flipped over. What aisle is that? Right? You can tell things upright. So upright, reduced, virtual images for the concave mirror. Now, I keep referencing that light from an infinite distance kind of comes to the focal point. That's true within a small angular aperture of about 10 degrees to either side. If that angle gets any bigger than that, the rays that strike the mirror further away from the principal axis, they actually miss the focal point. They're close to it, but they miss. So you get this fuzzy bright spot near the focal point of most concave mirrors. Well, what do we call this phenomenon, this fuzzy bright spot? Spherical aberration. What is it, class? Spherical aberration. Is that fuzzy bright spot formed near the focal point? Now you could correct the spherical aberration by not using a concave mirror to focus light rays. There's a better shape, not a spherical mirror at all. Parabolic mirror. Remember we looked at the parabolic reflector on that video we watched of how they can have a tube of oil of some kind right at the focal point of the parabolic mirrors. So as the sun's rays come in, they're all focused on that oil, heats the oil up very, very hot, which, as the oil passes through the water, boils the water, causes steam, steam turns turbine, turbine produces energy. Solar power. Not as efficient as solar cells, to be fair, right, that you talked about in physical science, but cheaper in the long run because you never have to replace anything. The oil just keeps flowing through, never has to be changed out. There's no decay or, okay, we've run out of electrons to produce from solar, Anyway, but parabolic mirrors have a perfect focal point. We also looked at it from the perspective of like a mag light, right? You change the size of the beam as you turn the end of the mag light, cause the beam to be wider or narrower based on the positioning of the parabolic reflector. Questions on all of that? Any of those terms, say, can you hit that term again? Okay. Convex mirror, store mirror. You'll look at it. The image you see, class, is virtual in the mirror, upright, reduced, or side passenger mirror of car, right? Objects in mirror are closer, from your perspective, side mirror. Objects in mirror are closer than they appear. Why? They're virtual. You can actually see them inside the mirror, upright, reduced. Concave mirrors, infinitely far, you just get a speck. Bring it closer, you get a reduced, inverted real. At the center of curvature, unmagnified, same size, but still real and inverted. In front, enlarged, still real and inverted. At the focal point, none. It's nothing there. Come in front of the focal point, virtual, upright, enlarged image produced. All right, clear, yes, except for a clean sheet of paper and a pencil. Clean sheet of paper and a pencil. Don't need a calculator, no math on this quiz. There will be math on the next one, but not on this one. Clean sheet of paper, pencil, and everything else away. First one's name at the top of your paper, along with today's date. This is 3/27/23. 3/27/23. Some people would say that's an odd date for a quiz. Thank you, Audrey. I appreciate that. People on YouTube are like, don't encourage him. All right, 3/27/23 today's date. This is quiz 24A. Quiz 24A. Quiz 24A. Let's take a look at the quiz together very quickly. Numbers 1 through 10, completion. Write the word that best completes each of these statements. Numbers 11 and 12, you're writing out a couple of things. Number 13, you're listing some things. Number 14, answer the question. Then for numbers 15 through 19, there are 3 sets of parentheses. You are going to choose one word from each set of parentheses. Okay, any questions on that? All right, take your time, do not rush through the quiz. All right, we'll come back after you're finished.